Great. Good morning. My name is Eric Siebert from Hewlett Packard Enterprise. Joining me is my colleague Charles Tierney. I'll be covering the VVol portion of this session, and Charles will be covering containers. So we got a lot of content, a lot of technical deep dive stuff we're going to do, so we're going to dive right in. And before I start, though, I always like to ask, who's actually using VVols today? And that, I know these lights a little hard to see hands, but it's every event I go to, VVols has been out for about a year and a half now, and every event I go to, see more and more hands in that. So it's good to see, the adoption starting to rise when people can understand the benefits and all that and what VVols is all about. Standard disclaimer here, some of the things I'm going to cover, particularly around replication, are still under development. So VMware had me add this just to cover the content I'll be talking about replication. Before we begin, just kind of want to show how long we've been working on VVols and that. We've been a design partner with VMware and a reference platform, and for about over 5 years now in that, and we continue to do that. So there's been a lot of work we've done with VMware and that to get this as VVols to develop, to production and that, and get it GA'd in that, and that's an ongoing process in that as we work to kind of improve and mature the VASL spec. That is what makes up VVols. So, why do we even need VVols in that? Wasn't VMFS great and that? It's worked fine for many, many years and that. Everybody uses it. There's really no huge issues with it. But there are some challenges around that, especially as we get today in more of an app-centric world and that VMFS is very LUN-centric. We're pre-allocating storage. We're carving up our arrays into silos. From the storage array perspective, we can't see inside a volume. So we can't actually see those VMs and be able to interact with them. Efficiency, we're over provisioning, more admin in that. We have to admin basically on two sides, the vSphere side and the storage admin side. Reclamation of space is difficult, trying to get space back when things are deleted or moved. We're using hardware-centric tools a lot of times to manage the vSphere storage. Provisioning long, and the key thing there is also our data services aren't aligned at the VM level. They're aligned at the larger block level or the LUN level. And that. So what VVols does is it goes from that LUN-centric architecture to more a VM-centric. We're not creating any silos within the array anymore, and that we're kind of basically aligning all the features and capabilities we have within the arrays directly to individual VMs. Everything's dynamic with VVols, so we're not pre-allocating anything. Basically everything is automatically dynamically allocated when we're creating VMs. We're able to automatically reclaim space whenever that's needed as well. And it's a lot more simplified. We're only doing management really on one place on the vSphere side, which I'll talk about in a minute here. So what it allows us to do is have that, previously if we want to do anything on the storage array, if I want to replicate or do things like a snapshot, I had to do it at the entire LUN level. So maybe I didn't want all those VMs in that snapshot. Maybe I didn't want to replicate all those VMs or apply a certain array feature to all that. But I couldn't see VMs, so my array features aligned basically with an entire data store. With VVols, that all changes now. So I can pick and choose kind of a la carte. If I only want to snapshot these 3 VMs, I can do that. If I only want to, replicate these VMs, I can do that and put VMs on different tiers of storage. So it really allows us to get a lot more granular with what we can do as far as aligning those storage array features to virtual machines. And so what happens here is, we're not putting the storage admin out of a job. Essentially, we're shifting the management of storage from vSphere, or from the storage array to the vSphere admin through a lot of automatic, dynamic type of automation that's as part of this whole VVols thing. On the storage side, we're also offloading to the storage array a lot of the functionality that we traditionally have done in vSphere. Things like thin provisioning, we've always been able to do it on vSphere or the storage array. Things like snapshots, we've always been able to do that on the vSphere side or the array side. So now a lot of that shifts. So all the kind of common tasks and all the storage functionality is shifting to the storage array, and the management shifting to the vSphere slide. So it's really empowering the vSphere admin to be able to provision his own storage, to be able to do array snapshots and things like that through the automation that's kind of built into VVols and policy-based management. So talk about the architecture, because this is way different from what you know with VMFS. All these components are basically new with VVols. The first component we have is the protocol endpoint. And that is a logical I/O proxy. Essentially, that's my data path between all my hosts to the storage array. There's typically a single protocol endpoint within the storage array that all the hosts connect to. The spec does allow for more, though. And essentially, all my data traffic is going to go from from the host to that protocol endpoint. I'll talk more about that, what that actually is in more detail in another slide. The VAS provider, that is our out-of-band control path. So certain operations we do with VVols require us to go through that VAS provider component to do things like looking up sub-LUN, secondary LUN IDs on the storage array to bind to VVols and that. So that VAS provider can be either an internal or an external VAS provider. Internal meaning it's embedded within the array. External meaning it runs the virtual appliance. And really it's up to each vendor on how they want to implement that. They can implement it either way. With 3Power on our side, we've actually put that within the storage array just for a little bit more resiliency and not having an external component to manage. The storage container itself, this is the pool of raw storage capacity. Now, there's nothing pre-allocated with a storage container. It's not like VMFS where we got to create a LUN and then we got all that storage within that VMFS volume. A storage container actually has zero capacity inside it. It's simply a logical entity within the array that our virtual volumes go inside. We can have multiple storage containers on the array, but there's nothing really we're allocating there. Everything's dynamically allocated at the VVol level. The virtual volumes themselves, and we'll talk about more about the different types of VVols in another slide, but essentially these are the containers. What they've kind of done here is taken some of the traditional files we have with VMFS, our VMX files, our VMDK files, all those different types, and they encapsulate them into a virtual volume that is able to be written natively to a storage array. We're not using a file system anymore on the storage array, essentially. We're writing data natively. vSphere has a capability with this to write data natively to the storage array. And then storage profiles. You're familiar with, vSAN. vSAN's had this for a while, where we can create storage profiles on the inside of vSphere and put the array capabilities and features within those and assign those to virtual machines. And I'll talk about more about that in a minute as well. So one thing that happens with VVols is, what's a little bit different from what you're familiar with today, is we have to, when we turn on VMs, power them on, we have to bind to them and that. So VVols essentially live as sub-LUNs, secondary LUNs on the storage array, and we do that bind operation when we power that on. So the way that works is we're first connecting, the host will first connect to the protocol endpoint. That establishes that data connection to the protocol endpoint. Next, we have to figure out, okay, so I have my VM, what are the sub-LUNs for that VM? So I have to ask vCenter for that information. The host can't do that directly today, and that's called an out-of-band bind. We're binding out-of-band, meaning we have to go to another entity to find out that information. Eventually, the spec allows for bringing that in bind, but today it's still out of bind. So we ask vCenter, hey, I need the sub-LUNs that are associated with that VM. vCenter is going to query the VAS provider, find out those sub-LUN IDs. We then know them at the host level, so we can then bind our VMs to those virtual volumes, and that operation essentially happens when we power on a VM, and then we unbind them when we power off a VM. So more on the protocol endpoint. Why do we need a protocol endpoint? And why can't we just connect directly to these secondary LUNs? And PE was created. This was new, some new stuff that VMware added to the T10 specification for SCSI, specifically to allow this type of kind of sub-architecture. The PE allows us to address the scalability that we have with VVols, where we're used to working with LUNs in the hundreds, and now with VVols we have to work with these sub-LUNs in the tens or hundreds of thousands in that. So there's a lot more objects on the storage array that would potentially be visible to the host. And, having to have the host see all those many LUNs just doesn't, we run into SCSI limits. How would you like to do a rescan on a host and have 20,000 LUNs to go through in that? So basically the protocol endpoint is a single LUN. So it sits in the storage array. There's no storage allocated to that LUN, though it's a special kind of LUN. It's essentially just code within the storage array. Essentially, it acts as a multiplexer, a proxy, and that. So my host connects to that, and from there, I connect to my sub-LUN. So the connection isn't direct to the sub-LUNs. I'm going through this protocol endpoint to get to those secondary LUNs. So the protocol endpoint, if you do a rescan on a host, it can be discovered at any time. It's going to show up as a LUN, even though it is a special type of LUN. On our implementation, we set the LUN ID at 256, kind of one above the traditional 255 LUNs that are supported. And what distinguishes it differently is there's a special LUN conglomerate bit that's set on that LUN, and that's part of the T10 spec, which identifies it as an administrative LUN. And that, so essentially, no storage there, but essentially it acts as my admin for my secondary LUNs beneath it. When we bind, again, we're creating those sub-LUNs, and just because there's sub-LUNs, though, doesn't mean performance is going to be any different than a traditional LUN. All those LUNs still have its own paths, I/O queue within the array, and that. So there's no really degradation or overhead associated with doing this. The host itself has its traditional single queue that it's had with per protocol endpoint. And all that I/O on the host goes through that queue. The queue depth was increased because of VVols, though, because a lot more kind of traffic going through that. But we've done testing, and we found a single protocol endpoint to be sufficient to handle all the I/O going through and not become a bottleneck. So let's meet the VVols. So the first one is config. Every VM will have one of these. Essentially, think of it as your VMX file that you have with traditional VMFS that had all the virtual hardware data, how we made up the VM, as far as, all the components that virtual hardware we put in there. This is, again, a wrapper around all that stuff. So we have the VM config data in there. We have disk metadata. We have log files. Lock files, all that's within this config VVol, and that's provision thin by default. And this one's a little bit special because this one's actually formatted. It's the only VVol that's formatted with VMFS. So we got the VMFS file system in there, which kind of is the bridge from VMFS to VVols, where if you look at a data store browser and you look at a VM in the vSphere client, and it's a VVol VM, you're still going to see those traditional files that you see today, and that VMFX, VMDKs, and all that. The view there will look the same, but on the back end, they are actually VVols in that. But I think because this is formatted VMFS, it still gives you that same viewpoint on the vSphere client side. Max this file can grow as 4 gig, and it's automatically truncated by reducing log files once it reaches that size. The data VVol is similar to your disk files, your VMDKs. Essentially, it's just your raw virtual data for the VM. We also use this type for snapshot VVols, and that. So anytime we take a snapshot, another one of these is created and then deleted once that snapshot's removed. Again, provision thin. Max size is the max size virtual disk, 64 terabytes, and there'll be one for each VM disk and snapshot. Swap VVol, that's similar to your vSwap file that you have today. What gets created when we power on a VM for memory over commitment, we ever run out of physical host RAM, we got to swap to disk, and this is created for that purpose. It's created automatically when the VM is powered on, just like it is with VMFS, and deleted when the VM is powered off. It is provisioned full, which is simply because it's serving as memory. We want that to be pre-allocated for performance reasons. 1 per VM, and the max size is in line with the max size of RAM you can assign to a virtual machine. Your memory, final one. Similar to if you're storing a memory state, you're suspending VM, you're saving the memory state, or a snapshot with memory state, this is essentially where that is stored in there. And there is one other type, the other type, but nobody's really, that's not really being used today by any vendors that I know of. So from the array side, what do VVols look like? So if you're familiar with VMFS, you can go in, you can see the subdirectories, all the files within there, look and interact with them, but VVols is a little bit different. There's no file system on the storage arrays, so you can't really do that. So what we did was develop some command line tools that allow the storage admin to be able to see and interact with the different VVol objects and components like the VAS provider. So this is just a look of what we've developed and how that appears. We could see the VMs, and we could see the state they're in, the number of VVols they have, and the number of the capacity-wise, what they're using physical and logically. And then further digging in, we'll show you the individual VVols. Now, they're all in one big, so if you have hundreds of these, it's one big listing, essentially. There's no directories. But you'll see the different types of VVols as well, and how they're provisioned in there. But again, this isn't meant to be managed or interacted with on the storage array side. If a storage admin goes in here, tries to do something with these files, it's going to mess up vSphere, because vSphere is not aware that that's happening. So storage policy-based management, the real kind of the layer that kind of brings us all together, and that essentially what that does is The array is going to, and if you're familiar with the 1.0 version of this, the array kind of did this with VASA 1. It was very crude, rudimentary. We passed a whole string of capabilities over. Wasn't very usable, or you couldn't really do much with it. But now with the new VASA, we can pass along individual array capabilities. So the array is going to tell through the VASA provider vCenter, this is everything I'm capable of, and that will include things like the hardware, what types of drives they are, what type of RAID levels are there, any features within the array that are supported with VVols, so encryption, thin provisioning, caching, performance features, all get advertised up through this to the storage array. Then on vCenter, essentially, we presented a menu to vCenter. So now I can go create a storage policy and pick and choose whatever I want within that policy. So I may have policies that line up with different, performance aspects or availability aspects, gold, silver, bronze, that have different types of hardware capabilities and features within that. Once I have those built out, I then assign them to virtual machines, based on what the requirements are for that VM. It's a dev one. I may put them in my bronze policy, my production SQL server in the gold policy. And then it's up to the storage policy management engine in vCenter to ensure that those VMs are on the appropriate tier of storage and it maintains compliance there. And this is what that looks like on the vCenter side. It might be a little hard to see, but essentially when you create that policy, you're going to see all those capabilities come up. And then you can pick and choose from the different, we call them common provisioning groups, but the different types of drives within the array itself. We actually have the capability of putting snapshots on a different tier of storage if you want, the array-based snapshots for that VM. And then other features like thin provisioning and that. We all you just pick and choose what you want to build within that policy. So snapshots, changes a lot and for the better. And there's actually a whole session on snapshots here that talks about this in more detail. But snapshots were always a pain point for the vSphere admin, and that you got snapshots running on the host. They're resource intensive. If you leave them out there too long, you got to commit all that data back in there. It takes forever. So changes a lot with VVols. If you're familiar with traditional VMFS, what would happen is we take a snapshot, our base disk is frozen, we're not able to write any more data to that base disk, it's read-only. These snapshot VMDKs get created, so all new data is written to the snapshot VMDK files. And then when I go and delete a snapshot, that's when the pain begins, because now I got to take all those, roll those back into my base disk, and if it's been out there for a long time and I have a big snapshot chain, that could take hours and hours to complete, resource intensive as well, and that. So with VVols, that changes for the better. So now when I take a snapshot, what happens is my base VVol remains active, read-write, and that I'm not freezing that disk anymore. So essentially any changes that come in, that data will be written to the base disk, but the original data will be written over to a read-only snapshot VVol. So why this is good is now I got to delete that snapshot. What happens? I just throw away the snapshots. My base disk is already has all the active data. I don't have to roll anything in back into that base disk anymore. So a lot quicker. And Symantec actually did a session last year. It's available now if you go to the sessions from last year that they did benchmarking on the impact of this, because you have to take a snapshot for every backup you do at the beginning of that process. And they were seeing windows shrink, as much as an hour, backup windows, because it was so quick, the backup agent doesn't have to wait for that commit process to go back in. So a big advantage there is, your backups will definitely improve. Some other advantages is, it's just a lot more efficient doing this on the storage array instead of bogging down the host with doing snapshots. There's no host resources required. We're not waiting forever for these things to commit. If we have a long chain of snapshots, there's no chance of something breaking and losing data. The base disk remains active, and performance-wise, it's much better on the array. One thing I'll note, though, is these being array-based snapshots, you're still taking them the traditional manner. So you're still going to the vSphere client, you're still snapshotting that VM. That doesn't change, it won't look any different, but on the back end, these are all array-based snapshots now. vSphere is no longer capable of managing snapshots on its own on the host with VVols. Another great thing with VVols is the way provisioning works in general in that. So we're not pre-allocating any space. When I create a VM, they're thin provisioned by default. So what will happen is I'm going to create my data VVol. It'll be thin provisioned. And that thin provisioning is, again, an array-based feature. We don't have the option of doing it any longer on the vSphere side. You can still choose thick if you want. It's in the VM settings, but for most use cases, you want it's going to stay thin. The big thing here now is, if you remember space reclamation, unmapping, that came out in vSphere 5, being able to take space back whenever a VM was deleted. It was designed to be automatic initially, and VMware had to make it a more manual operation through the CLI that had to chug through the whole array to reclaim space. But now we can see VMs as objects. So me, Mr. Storage Array, knows exactly when that VM is left. So I can say, take that space back right now. So big advantage here is I automatically reclaiming space right away. And I no longer have to do an unmap operation to be able to go through and chug through and try to reclaim space. It's all automatic now. Once I delete my VM, the VVols will be deleted on the storage array. And then on the storage array side, we know what blocks those VVols are on, so we can reclaim those right away. So big efficiency increase in there where we're not having to manually go out periodically and try to reclaim space. It's all dynamic and automatic. Same with provisioning. So big win there for VVols is all that automatic and dynamic provisioning. Animation here. So another change, is between the protocols. So fundamentally, file and block on vSphere have been a bit different in how the implementations occur. The big difference is mainly being how it's representing data to the host. The file system is either vSphere managed or array-based managed with a file with NFS. How we're storing files, and the big one is, because with file-based storage, they've been able to see VMs as objects because they're written as file on NFS storage. Well, at the block level, we haven't been able to do that. So VVols kind of puts a standardized wrapper around how we're doing storage, regardless of the protocol now. So what changes with that is, the host adapter and my transport are all the same. That's not going to change. But my host present is going to be unified as a storage container on either block or storage. It's no longer a LUN or a mount point. Our file system is going to be vSphere writing natively to the storage array, so that changes. Again, we're not having a file system on either side. It's all vSphere managed. My VM storage is going to be VVols in that, so no longer VMDK files. That changes for both. And then my storage visibility in that. So now, finally, on the block level, we can see VMs as objects as well. So what VVols does is really set that kind of standard for all of us storage vendors, regardless of the protocol, to be able to kind of do things in the same manner. So it's a good thing for that everything is kind of unified, regardless of what type of storage you're running and that. But, beyond that, this works regardless with any of the protocols and that. So VVols supports all the standard protocols that are out there and that, but what changes is kind of how things are done under the covers. So some max limits between VMFS and VVols. A lot of this is the same, the disk sizes and things like that. One big one that changes is, if you're used to creating LUNs, we've had a max limit there on LUNs, 64 terabyte that VMware has imposed. With the storage container side, though, that's a ridiculously big number, 2 to the power of 64. So it's essentially a storage container is your raw pool of storage on the storage array. Now, we're not pre-allocating anything, so anything that's available on the storage array is essentially going to be within that storage container, unless you use, some vendors have tools that can allow you to maybe to partition off the array a little bit so it doesn't consume the entire array. But by default, in a lot of cases, depending on the implementation, you're going to see the storage container just using what's left on the storage array. Since nothing's pre-allocated, it's dynamically there, so whatever space is available will be available to that storage container. So the max VVols per storage array, that's really vendor determined in that. It's up to each vendor to figure out how well they can scale. This is a big change for block storage and that, again, we're not dealing with LUNs in the hundreds, so all the storage vendors, the block ones, have had to deal with increasing this amount of LUNs that they're supporting within their array. So I've seen this vary, ask your storage vendor what they support. I've seen it as low as 1,000 for some vendors. I've seen it as high as hundreds of thousands for other vendors and that. And that's really going to determine, how you can scale VVols on your array, because every VM has multiple VVols. So what your vendor supports is going to dictate, really essentially what you can fit within that storage array based on the number of VVols that are going to exist on that array. The theoretical max VVols in the vSphere cluster is 19 million if you did the math of the max virtual disk per VM times the max number of snapshots times the max number of VMs for vCenter cluster. Big number, you're probably never going to be there. The max VVols per powered on VM is around 2,000 if you again do the math. You'll always have one config, one swap. 60 data VVols in that based on the number of virtual disk a VM can have. 1,920 snapshots based on, you can have 32 times those 60 disks and 32 memory states. So a big number in that, but realistically, every VM is going to have 2 VVols, config and data. You're going to have a third when you power it on, and then from there, the number, their average per VM is really going to be dictated by how many snapshots are you going to take and how long are you going to keep those snapshots. Typically we see the average around 6 or 7 VVols per VM, but like I said, it's really going to matter on how you're doing snapshots and how long those are retained in that. So it's a key thing to know when you're planning your implementation of VVols is, understand kind of where you're going to reside and what's your kind of limitations around whatever storage you're using, that how many that's supported. And I've seen vendors create, I know we have increased our support over time to steadily increase that level of support for the number of VVols that we support. And I expect that to grow simply because, these environments are getting larger and larger and the array needs to be able to support, that number of volumes. So requirements and incompatibility for VVols. Requirements, obviously, the host must be running vSphere 6, and vCenter must be vSphere 6 as well. Array firmware must support VVols, so check with your vendor, and they may require a firmware upgrade to be able to support VVols. You must use a supported storage protocol, and this will vary by vendor. Check the VMware hardware compatibility list, and it'll show you each vendor and what protocols they support for VVols. I know with 3-part today, we only support Fiber Channel, as we're the Fiber Channel reference platform, but we plan to expand our support for protocols as well. But check the HCL, and it'll tell you what's protocol supported for each vendor. Your storage array must be capable in licensing to support thin provisioning and snapshots. We can no longer do that in vSphere itself. So before, if you had an array that maybe didn't have thin provisioning or snapshots, or you didn't have it licensed, you could do it in vSphere. But now we have to do it all on the array. So in some cases, you may have to license additional software within the array to be able to support those activities. The HBA driver, this one bites a lot of people, is it needs to be able to support secondary LUN IDs, sub-LUNs. And that was new. That was new added to the T10 spec. So all the HBA driver vendors had to go and add code to their drivers to be able to support this. I think now we're at the point where, VVols has been out for 1.5 years, where most of them support that. You may have to load a special driver file to do that, or download a special ESXi image that has that in there. But if you're running into problems with VVols not connecting to the protocol endpoint, that's your first culprit usually, is go and check to make sure that whatever HBA you're using supports those secondary LUN IDs. Incompatibility, things like RDMs, that's a pretty limited use case. You can't really do an RDM with a VVol, so that's not supported. Array-based replication, not supported again with the initial specification, but I'll be talking about that in more detail in a minute. Fault tolerance, NFS 4.1, storage I/O control, all are not supported today features. In some of these, it doesn't really matter that it's not supported, but in other cases, if you have a use case for RDMs, you might want to stick with doing that instead of moving that VM to a VVol. So here's a kind of screenshots of those hardware compatibility lists that I talked about. So virtual volumes, if you go in there and when you select the what are you looking for, that drop down, you can select the VVols list in there, and then you can then pick and choose, and you'll see all the different vendors in there that actually support that, and you can drill down further to see protocol support, what firmware you need for that, and what things they support, like the highly active VAS or the highly available VAS provider and things like that. So that's where you want to look to check to see if your array supports it. Now, your HBAs, there's a separate one. If you go to I/O devices, you'll see there in the feature, there's one called secondary LUN ID, which enables VVols. So check that. You can check your HBA that way to make sure it supports VVols as well. So how do we get there? You're on VMFS today. I want to go to VVols and that. So a lot of things you'll need to do just to make sure you kind of understand what you're getting into and what you have to do before migrating. Biggest thing is ensuring your backup applications support VVols. It needs to be able to back up those VMs. And one caveat with VVols that we can't do today is we can't do direct to SAN backups. That's something not supported because a physical backup server can't connect directly to storage like it used to with VMFS via the VMDK toolset that they have. We can't do that anymore. So if you're using direct to SAN backups today, that isn't supported. I suspect at some point VMware will have APIs and tools that allow you to connect a third party to connect to storage and see VVols, but today you can't do that. But said that most of the backup vendors support VVols today, regardless of the direct to SAN. Most of them all have support for VVols, but check. Ensure your array supports VVols. Do that firmware upgrade if you need to. Ensure your HBAs support VVols secondary LUN IDs. If you have an external VAS provider, make sure it's highly available. That's a key component of this whole architecture, that if that's down, somebody decides to storage vMotion it somewhere else or shut it down, I can't power on VMs anymore, power off VMs. My existing VMs will stay up and running, but the certain operations, like the power operations that require that VAS provider, won't work anymore until that VAS provider is back up and running. Ask your vendor, find out what array capabilities are supported in VVols. That's going to vary widely by every vendor implementation. It's up to the vendors to figure out what capabilities we want to send up and be able to put into storage policies. Understand your limitations and incompatibilities of VVols that I've talked about already. Know the array scalability and compatibility of VVols. Check the array features that need to be licensed. Time sync across your environment is important. We've seen a lot of errors that people have run into just because time sync isn't synced across vCenter, the array, the host. Plan out your storage policies in advance, and it's always best to just test this out. And that's mainly what we're seeing people do today, is try this out before jumping in that pool and going all in. So migrating, there is no easy button to get to VVols. You can't just click on VMFS and have it automatically be VVols. They're completely separate within the array. So really the only path to get there is we can run them side by side on the same array, and that essentially you would have your VMFS volumes, and whatever space is left on the array can be used as a storage container, simply because we're not allocating any space. So we can have those running on the same array together. But storage vMotion is really the only way of getting from VMFS to VVols and back, and that. So you have to either plan out putting new VMs into storage containers or plan out your storage vMotion migrations to get the VMs over there. It's recommended that VMs are using the latest hardware version 11, and it's recommended to delete any snapshots that are running on the VM side before you move that. And big one is do not put vCenter on vVol storage, and that, because you get the chicken and the egg thing. If it's down, I can't bring anything up until vCenter's up, because that's where all my VAS provider information is. So you always want to keep vCenter today until it goes in the bindings on either VMFS storage, physical, however you want to do it. Don't put it on vVol storage. Just a quick look what we support on VVols. All of our arrays support it. These are the capabilities that we pass. 128,000 VVol objects is what we support. And the feature sets you see there around thin provisioning, array snapshots, all these other ones are what we support that can be put into policies. We also support multiple storage containers and multiple vCenter servers. All right, so let's talk about what's coming. This is why I need the disclaimers to talk about replication, which isn't there today. It wasn't in the original VASA 2.0 spec, and that is to be part of the next release of vSphere, which will be the evolution of VASA into VASA 3. So what we'll be able to do now is replicate at the vVol level instead of the LUN level like we do with SRM. If you're familiar with SRM today, we're replicating entire LUNs over and that. And with vVols now, we'll be able to pick and choose on the array which vVols or which VMs we want to replicate over to another array. So the way that's done is we're creating replication groups. Those can be created, and again, this is kind of up to every vendor how they're going to do this. They can implement it and where the storage admin has to create these, or they can be dynamically created. But the replication groups will be my kind of container for the VMs. Whatever I put in that replication group, VM-wise, will get those vVols will get replicated to the other array. You can't have multiple targets, so if I did want to have my VMs go to different targets, this data center and this data center, you can do that. The fault domain is kind of the next wrapper above that. With us, it's basically the storage array is the fault domain, but that can contain multiple replication groups if you want to define multiple groups that essentially are going to fail over together. And then availability zones is the zone above that, and this just kind of shows how you can create those replication groups, fault domains, and multiple points of replication from your primary to your kind of secondary data centers there. So how are we implementing this? So there's something new with storage policy-based management in the next release of vSphere called components. And what a component is essentially is it's something I define once and I kind of reuse in multiple policies. So I don't have to actually go in every single policy and do this. I can build out components based on replication, then add them already predefined into policies. So in the next release, you'll see there'll be something there called create storage policy component. And that essentially is where I will pick my type of component, be it, there's different types there, replication, encryption. If you didn't know, encryption is also another feature, VM encryption coming soon. There's a session on that, I think, today. But compression, inspection, caching, performance, that's where you'll pick that. So for our case, it would be replication. We pick that type of provider that we're using. And then we build out our policy rule, essentially, and we'll put in things like, where our targets are, what type of disk there we're going to put it on, the type of copy mode, either periodic or sync or whatever, and then our RPOs around that. So that's how I'm going to build out my policies for that, for replicating my VMs. And then we're going to add that, when we built out those components, we're going to add that to the storage policy. Storage policies can have multiple components added to them. One might be replication, one might be encryption. So I do that, and then, once that's there, essentially, when I'm creating a VM, you choose your storage policy, and then below that, they'll have a replication group. So there, essentially, you choose a replication group, or it can be dynamically created if it's automatic on there, and then essentially that VM will be part of that group, and then we'll be replicating however the components in that are defined to whatever other destination is set up there. So replication is great. Hey, now we can finally replicate those VVols over to another storage array, but what do I do next? How do I actually utilize that in real life? Be able to fail over, get my, I got all my data over to this other data center, but what happens if something happens and I got to get over there to fail over to it? So all the DR operations with this implementation are designed to be managed and performed on the vSphere side. Similar to SRM, where you have everything, you have SRAs that kind of handle the array replication. With this as well, it's all designed to be kind of failed over and managed on the vSphere side. Orchestrator will not initially support VVol doing this, VVol DR automatically. That'll come at some point. So basically with this initial release, the way you would kind of fail over is there's scripts that you can write that would do some of the action that traditionally Orchestrator may do using the new APIs they have around this that allow you to do failover. And the types of operations you can do are things like test failover, failover itself, planned or unplanned, reverse recovery after a failover. You have to configure storage containers on both sides and before creating these replication profiles. The groups on the storage array, so our remote copy groups on the storage array are all managed on the VAS provider side. It's not designed for your storage admin to go in there and manage these. It's all managed automatically through all this workflow. Again, and all vSphere operations are all managed on the vSphere side as well. So despite we're using array-based replication to do this, all the management's designed to be on the vSphere side, similar to like we do with SRM. And this is just a sneak peek of what we have coming up in our 3-part OS. So traditionally we've had the management kind of under the covers via the CLI, but we're going to be moving that to our GUI just to really give the storage admin visibility to understand what's going on with VVols. And then instead of going to the CLI to see all those objects, this gives them visibility to these things. You can manage. The only thing you really do on the storage array side would be with storage containers. So you can create storage containers here, and then you can also see info now around VVols. How many VVols are with that VM, how is it provisioned. You can see replication info in there, virtual machine info in depth, all the VVol files, how replication is, being synced. You'll see the storage policy information. So again, this is really designed just so the storage admin is not completely in the dark. He knows what's going on within the array with VVols. We're taking essentially some of the common things he's doing back. So this gives him that window into being able to see actually what's going on, so he can keep an eye on what's going on within the array. Another one is showing the replication info so you can see when that is synced and whatnot. So VVol adoption in the real world. A lot of people we're finding are just testing it out right now and that. But we have talked to a number of customers that have large-scale implementations planned. Some of the reasons for light adoption, despite a year and a half down the road, is customers aren't on vSphere 6 yet. I've talked to a lot of people, and a lot of people are still on vSphere 5. That lack of replication support, people aren't sure what VVols is. Right now or back, at the beginning there was limited scalability and feature support, and there's really no easy migration path. We expect that to change pretty soon, actually, and it's been out for a year and a half, but replication will finally be here. It'll be more matured, and you'll see a lot more increased scalability and feature support. And I think, just like today, I'm giving you kind of an understanding of what it's all about and the benefits. More people will know that and see that and realize and migrate to VVols. So the top reasons to start using VVols now, you don't have to go all in. You can use it right alongside of VMFS and that. So it's not all or nothing. We can go back and forth with storage vMotion. You get that early experience, Did you wait forever to switch to ESXi or the vSphere web client and that, and get it early in there so you understand it and not kind of learn it at the last minute. Get your disk space back. Everything is automated as far as provisioning and reclamation. So big win there is staying thin on the array. It's available in all vSphere editions. This isn't a feature. This is core functionality architecture in that. And, VMware hasn't stated it, but they never keep two of anything around. At one point, this will replace VMFS, I imagine. Let the array do what it does best in that. It's a storage I/O engine, and it can do a lot of these resource-intensive things better than vSphere can on the host. Start using storage policy-based management now. Essentially, it's been in vSAN for a while. Now we finally have it for external storage through VVols. And snapshots don't suck anymore. It's great in vSphere. We can have the array do it. We don't have the overhead. We don't have to worry about all that extra stuff we have. So backups will complete faster. It's easier for generalists. We're not managing things in two places. We're just managing it on the vSphere side. And one architecture, like I talked to before when I compared file versus block, they're essentially on the same plane today with VVols because the VASTA spec kind of dictates on what we have to do. And the big reason is the VM is finally a unit of storage. We can see, and this is what it's all about, we can see a VM, interact with it, and apply array-based features directly to VMs. So that's it for my portion. Just briefly here. And if you want to know more about it, we have it running in the booth. So stop by, ask questions. I'll be available after if anybody has any questions as well. I'm going to bring Charles up now, talk about containers, and thank you for your time.
Every container's presentation is required to start with a picture of a ship with containers on it, I've discovered. Thanks, Eric. He's a hard act to follow because he's extremely technical and better at this than I am. So I'm going to talk about containers and some new things that VMware is doing, which is pretty interesting stuff. I'm going to introduce container-based virtualization, let you know what it is, where it came from. I'm going to talk about VMware's new work on VIC, and I have a little bit of late-breaking news from the keynote this morning. And then I'm going to cover the storage aspects of containers, how you use persistent storage with containers, and explain what persistent storage means in that context. And I'll close just by covering several customer examples of container deployments. Okay, well, the quote here is from Isaac Newton. If I have seen further than others, it is by standing upon the shoulders of giants. Nothing in the world of IT was built by, generally was built by the person you're just seeing it from. It came from somewhere else. Virtualization is not a recent invention. It's basically been part of every OS pretty much from the beginning. It's definitely part of all modern OSs, and as you can see on this chart, it really goes back in time. You have some key points here in time. So OS level virtualization with Multics. Multics was the ancestor of all Unix versions and all Linux versions. If you look at machine virtualization, that was CP. CP turned into IBM's operating systems. So VMware picked up that work from Multics and from CP and carried it forward. Did something very interesting with it and very revolutionary, I think. And has been in the business ever since of just really good execution on product. Look at the whole space in the 2000s with the Linux pieces, a lot of that early on was driven by Google trying to solve the problem of massive scale. How could they live with this just massive, horrendous scale that they had? They built a new architecture, OS level isolation, and then they applied that to their Linux, and then they standardized that and gave it back to the community. So when you get to Docker, what the Docker guys did is they picked up all these pieces and they packaged it a little bit differently. Their aim was simplicity, build a powerful, simple platform. And now let's go look at what containers look like. So I think everybody here knows what a virtual machine looks like. So let's just look at containers and the differences. Probably the key difference is that there's a container engine. The container engine on the virtual machine side is just because we happen to be running containers in a virtual machine over there. But on the container side, the container engine is part and parcel of what defines a container. You see the OS in there. The OS is shared across the containers. Now, as it turns out, I'm showing this on Photon Platform. And in Photon Platform, the container engine and Photon OS are both built into Photon Machine. So if you take those out of the picture, what you're left with in the container is the application and its dependencies. That's pretty much what defines a container. The application and anything that it depends on to run properly in whatever environment you happen to be choosing. We'll talk a little bit more about Photon Machine and about vSphere and containers in a little bit. So why are containers so popular? They've become wildly popular, and you usually run into containers in the context of DevOps or web scale. Netflix uses containers, Uber uses containers, Google uses containers. These guys who are massive scale, have massive scale problems, end up using containers a lot. But at heart, what it does is it gives you agility, portability, and control. So the agility for your development teams to use whatever tools they need to use to do their job. So this is just a selection of tool chains. There's a lot of different tool chains that you could use that are fully containerized. And many system environments. Just as a simple example, lots of people develop on PCs, lots of people develop on Macs, and typically they have QA servers, staging servers, build servers that are some other architecture. Doesn't matter with containers. Let's look at the IT side, the control side. So the IT guys need their applications to run invariably on whichever platform they're using. So it's a similar kind of problem, but from their perspective. And the solution is, of course, a shipping container. So package your app so the developer puts things into the container, build it, put it in the container. The IT team picks up the container and manages the containers and runs what's inside of it. It's build, ship, run. Very simple. And that, in essence, is why containers are becoming so popular. It's powerful, it's lightweight, and it has a lot of isolation that comes with it, so the environment works very well. Now let's look at vSphere's new environment. They gave me a little bit of late-breaking news today, so it was nice of them. So they've announced the beta program for this, so vSphere Integrated Containers. They're going into beta soon. And so they have a method for people to sign up for this. They showed this last year at VMworld, and implementing it in a rock-solid, enterprise, scalable approach turned out to take more time than they thought it would. So that's why they're just approaching beta now. But you can see that essentially we have a vSphere Integrated Containers engine in there. We have a virtual container host, which is connected to a vCenter server. And then we have the other elements. So we have Photon OS, the container engine, which can be part of the ESXi server there. So essentially, the way this works is that you provision a container as a VM. So you build a container VM. It's actually very elegant. So it's tuned to minimize startup time and size. Container VMs are very similar to containers, but they're not exactly the same. There are some differences, and those differences can be important to understand. So if you're going to use these, you need to understand that. And the way that a container VM launches is kind of interesting. So the virtual container host receives a Docker run command. It downloads any new image layers that it needs. It sets up the IP address and any network mappings, and then it fast boots a Pico, extremely small container VM on an ESXi host. It creates any VMDKs and attaches storage volumes. Then it starts the VM. The container VM on starting immediately executes an entry point command, which in essence pulls the whole container environment down on itself. So what you have now is a VM, fully functioning VM with all the process mappings and connections intact, and then there's a container in the middle of it. So you have full vSphere integration in addition to full compatibility with container software like Docker. And if we look at the Photon platform, it's actually much simpler. It's a true bare metal platform, which means there's no virtual machine involved. That's kind of the industry definition of bare metal in this case. So Photon OS and the container engine, again, they're part of the platform. So this is very small, very lightweight. With the Photon controller, what you get is the ability to connect up as a management plane, an orchestration plane, to external orchestration engines, which, as we'll see, becomes very useful. So let's look at storage. So a lot of containers don't particularly care about storage. The container starts up, it opens a pipe, it gets information, it performs a transformation, it sends it out the other side. I don't care. I die, I don't care. They launch 10,000 of me because of my Super Bowl commercials coming up. I don't care. No issues. But increasingly, as enterprises start using containers with enterprise applications, they start looking at their enterprise data sets, and now I care very much about my data. And I need my data to be where I left it. If I'm the back end of a message queue, if I am a database, I need to understand that the transaction that I wrote just before I died is there and where it is. So that's what persistence is. So essentially, when a container starts up, it has these stacked layers, these image layers. These are pulled from a repository. They're managed by the graph driver, which is part of the container engine or the Docker engine. And this slide, by the way, this applies to Docker, which is predominantly what you're going to see, but there are other container engines. And all these layers are copy on write. You can extend the file system domain by adding file system drivers. And there's a lot of those drivers available. But typically, what's very popular is to use the Docker data volumes mechanism to manage persistent storage. So you have Docker data volume plugins, which extends the mechanism. You have plugins available for file, for block, and for object. So you can do pretty much anything that you'd need to do through this Docker data volumes and the plugins mechanism. The one below it, Docker data volume containers, is not so popular anymore because it was a pretty specific use case, and the ones above it tend to have taken that over. So let's look a little more closely at vSphere integrated containers and how they deal with storage. So we have our VIC environment. With VIC, I have my container in there. My container can use any of the vSphere pieces. So I can use vCenter's storage policy management. I could use VVols if they were available. I could use VMFS. I could use whatever I want in the vSphere space, right? But I also have access to all the container persistent storage mechanisms. I can use all the Docker tools in there. So what it comes down to is how you're going to be using your container environments. If your container environments are going to be used pretty much in a vSphere environment, then by all means use the vSphere mechanisms that can add efficiency in a vSphere, in a VMware environment. If you're using your vCenter, your vSphere environments to also host containers that run on other environments, then you probably want to stick to the more classic container setups. And let's look now at the same, pardon me. Let's look now at the same picture using Photon Platform. So this one I'm going to build and just provide a little bit more detail about how the Docker data volumes and the plugins work. So we have our bare metal machine. Let's provision a couple of containers and the Docker daemon to control those containers. And again, this is completely within the containerized environment. And now I have a container, and the container has requested persistent storage. It has requested access to its volume. So Docker will instantiate the Docker data volume chain and point it at the storage. Now I'll load the driver. The specific plugin that I'm going to use is my 3-part plugin, because why not? And so now I have the specific driver in place. And the only thing that remains for me to do is establish the mapping and start the container. So all that happens on the interposition. The container starts, it makes a request for storage, it's interposed, the Docker daemon sets up the mappings, turns the container on, and then it's running. Now, if the container died, that mapping, and it started up again somewhere else in the same cluster environment, that mapping would be restored. Because the mapping would be found, the Docker daemon would find the mapping and restore it so that the data would become automatically available to the container. So it's pretty useful. So you can use our particular plugin uses iSCSI right now. It can talk to our storage arrays, and it can talk to our store virtual software-defined storage product. There are a lot of other plugins available too. Now let's look at a couple of customer examples. So this is the classic infrastructure optimization example for use of containers. Typically, enterprise clean sheet deployments, if you're going to completely re-implement some part of your IT infrastructure and you don't particularly care about the legacy elements that you have, then you would use bare metal. But typically you wouldn't use one of them. You'd use like 500, each running multiple containers, some of which have persistent storage mapping, or you'd have 1,000 or 2,000 or 10,000. I've seen customers talking about thousands of bare metal systems. In this kind of environment, orchestration and management becomes just about the most critical thing. So orchestration and management is critically important. At scale, you must be able to provide good solid orchestration. Photon Platform integrates with the key and most popular storage environments. So Pivotal, Cloud Foundry and Diego, Kubernetes, Mesos Marathon, and Docker Swarm, the most popular ones. These all work in the VMware environment. They work in VIC, and they also work on Photon Platform. Let's look at the next case, which is, if I can't do a clean sheet approach, then what I end up needing to do is integrate with all the pieces that are available. This is HP's IT production environment pilot that's running with containers right now. And in this case, we just use Docker Data Center to provide the integration links into all the services that we have. So I don't want to cover this any more than that because it's complicated. And just in closing, I wanted to talk a little bit about big data and more to the point, data management. So here's a full-bore big data environment. This is a real customer's environment. They are a use case for big data for Docker. They're a financial services company. They have massive amounts of data that they've been collecting in this containerized environment for a couple of years, and it has all the regular tools associated with it. But when you're building this kind of environment, I think the key thing to understand is think about the security. You're touching your enterprise data. Just make sure that your security people are at the table when you design it. Make sure that the compliance people are at the table when you design it. In this case, these guys did exactly that. They designed the system around an integrated access management portal. Nobody touches their data unless they go through that IAM mechanism. And the data might have specific requirements on it. So let's say it's German consumer credit card data. You might not be able to move it out of Germany, in which case you need the data management hub to really understand, track the data, and make sure that any limitations are covered. And that's it. Eric and I thank you.